Assalamualaikum and hello everyone. So I would like to continue the discussion on the tutorial for heat exchanger. So this is part 2. Okay, let's start with this one first. Okay, this one I think you have seen in the previous part, in the part 1. And we have seen that from this question, we have analyzed is it necessary to multiply with 4 for the 2 for heat exchanger here? So it is, the answer is, since from the question, the total length is given as 60 meter and this is clearly specified in the question. So you don't need to multiply your answer with 4 for the length because the length given is the total length. Okay, I just want to highlight the one that I have missed in the part 1, which is the heat transfer coefficient on the tube side. Okay, so it should be 160. So if you want to try this question, please do so. Okay, but I will not discuss further for this example. Let's go to the next example, which is example 2. And this example is actually taken from Prof. Joshua video, which is the video of 37 at minute 19. Okay, so the question here is on the 1-8 heat exchanger, shell and tube. So 1 shell pass and 8 tube passes. So the tubes are thin wall. So remember, if it is thin wall, the diameter of outside diameter and also the inside diameter is equal, right? So it is made of copper. Sorry. The diameter given is 1.4 and the length of each tube pass is 5 meter. The value for U, which is the overall coefficient, is 310 and 10. And here we have water as cooling fluid, and this cooling fluid flows through the tubes at a rate of 0.2 kilogram per second. Oil as the heating fluid flows in the shell at a rate of 0.3 kilogram per second. So here the water and oil entered at the temperature of 20 and 150. So the inlet temperature for cooling fluid is 20 and the inlet heating fluid is 150. So determine the rate of heat transfer in this heat exchanger as well as the outlet temperatures for both heating and cooling fluid. So from here, you know that the outlet temperatures are not given. So if it is not given, then clearly the most easier way is to use NTU method. And here, if you compare this one with the previous example, which is this one, clearly from this example 1, you don't need to multiply the answer of the length because here the given length is the total length. But here, okay, here the length given is actually the length of each tube pass. So maybe I could show this. Okay, so the length of each tube pass. So that means here it is clearly given that the number of tube pass. So the number of tube pass is 8. So therefore, is it necessary to multiply it with 8 for 1-8 heat exchanger? So the answer is yes, because it is clearly given here that the length of each tube passes is 5 meter. Okay, so okay, so you don't have to confuse yourself. So this is the reason why Prof. Joshua multiply his answer with 8, right? In order to find the area. Area is A equals to pi dl, right? So maybe I could write. So area is equals to pi, the diameter d, and also length L. And in this case, specifically, Prof. Joshua times with 8 because L here for one tube pass is 5 meter. So for the 8 number of tube pass, you have to multiply it with 8. Okay, so clearly the number of tube passes is not the same as the number of tubes. Okay, so please be careful and please analyze your question more carefully, okay, and more critically so that you can make decision on how to answer the question. Okay, this is most important part because most of students, when they see the question, they tend to panic, and when they are panic, they don't give time for critical thinking, so they end up making the mistake which they shouldn't make because the question is actually quite straightforward. Okay, so let's have a look on tutorial 7. Okay, let's discuss on tutorial 7. So if you have further question on example 2, you can ask later. Okay, or you can discuss with your friend. So for tutorial 7, actually, I just want to expand the question in tutorial 6. Okay, so here it should not be CO5 because here is actually CO4. Okay, for our new CI, we have only 4 cost outcomes instead of 5. And for heat exchanger, it is specifically 4. Okay, now let's not focus on the cost outcome. Let's focus on the tutorial itself. So for tutorial 7, it is specifically mentioned that you have to use NTU method. Okay, or not? Oh yes, yeah. No. Here is actually redo tutorial 6. Oh, my mistake. Okay, here is actually tutorial 7, but it asks us to redo the tutorial 6 for the NTU method. However, this time, okay, for tutorial 6 NTU method, if you still remember, our problem was related to heat exchanger which has thin wall. Okay, but this one, okay, for tutorial 7, okay, we cannot neglect the wall because it's actually the heat exchanger tube is made of BWG12. Is the type or the standard of the tubes for heat exchanger. So what is the meaning of BWG12? So you can actually refer to BWG12 from this table. Okay, so since it is given that the OD is 15 mm, so you can find out about the ID, which is the inside diameter. So BWG12, and for 15 mm, the corresponding internal diameter should be 10.33. Okay, this is part that we have already analyzed so far. And the tube is made of brass. So this is the thermal conductivity of brass. And we need to determine the value of U, the overall heat transfer coefficient. Why we need to determine? Because it is no longer the same. Because last time, okay, for tutorial 6, you have thin wall, so you can neglect the conduction. You can neglect the resistance through conduction. But for this one, you cannot neglect the resistance for conduction because you have different diameter. You have different diameter. So between 10.33 and also 15 mm. So there is certain thickness of the tubes which you cannot neglect the heat transfer through conduction. So you must calculate the resistance through conduction. So therefore, then you have different value of overall heat transfer coefficient. That means you have different value of U. Okay, remember the value of U is actually equals to 1 divided by the, okay, U is actually 1 divided by area, oops, how to write this, area, okay, 1 divided by and multiply with the total resistance. It's not easy to write here. Clearly, it is not easy to write here. Anyway, okay, RT. Here it should be T. Okay. So 1 divided by area and total resistance. So this gives you the value of overall coefficient. Okay, so last time for thin wall, U is equals to 1 over H naught plus 1 over H inside. And you don't have the resistance to conduction. So for this one, you need to calculate the resistance through the wall. Okay, so it is given that Hi is 450, so this is the value for here, and the H naught is 200, so this is the value for here. So the question also asks specifically that you use one-to-one layout. Then here the question also mentioned that there are 200 tubes. Okay, there are 200 tubes. Okay, then because there are 200 tubes, okay, what do you think? Will the effectiveness will be the same or will the effectiveness increase? Right. So therefore, if the effectiveness will not be the same anymore, you have to calculate it. Right. Of course, it will be higher, right? Because if you have only one, then okay, let's say like this. So if I give you one task, okay, if I give you one task, and this task there is 5 parts. If you do this on your own, that means you need more time to finish it, right? But if you do this in the group, so of 5, so each of you do one part, so you can finish each task at the same time, so which means that you are more effective in this way. So therefore, we assume that if you have more tubes than one, then the effectiveness will also be increased. So therefore, you need to calculate the new effectiveness. Okay, so if the effectiveness increase, the rate of heat transfer will be different also. So this one also need to be calculated. Okay, then it is also asked you whether the outlet temperature will remain the same when using this kind of arrangement. And this one we will look later, the illustration of total thermal resistance if fouling occurs. Okay, now let's look. So this is the guided tutorial. So that means, first of all, you need to sketch the problem and actually to write down some assumption. So I don't write it here. So I think you know how to write down the assumption. So from here, this is the sketch for BWG12. So you have inside is the tube. Okay, I draw this not for 200 tubes, of course. I draw this only for one tube. Okay, and I don't draw the shell here because I don't need to use to illustrate the shell. Okay, so otherwise I need to draw 200 tubes in one shell. So then this is the information from the previous question from tutorial 7. So it is 5 meter long. Okay, so this is 5 meter. So when you draw, you need to label your drawings. Okay, so this is 5 meter. Okay, and it is BW12 with outside diameter 15 mm. So this is outside diameter 15 mm. And the inside diameter, as we have seen from the table, is 10.33. So it should be inside diameter here. So the tube is made of brass with a K of 100. So here is the thermal conductivity of the brass. 100. The convective heat transfer coefficient. So this is the H value because it is not the overall value. So it is the H value. HI and H out are specifically mentioned. So HI should be inside 450. H out should be here somewhere outside. It is between the tubes and the shell. So it is 200. And this is 1-to-1 layout. Okay. And it is also given the temperature. Okay, temperature of inlet and for hot stream and cooling stream. For the tube, we have, do we have it here? We don't have it here, but it is from the previous question. Okay, from the previous question. Okay, the temperature, inlet temperature for water which is coming in is 20 degree, and the rate is still maintained from the previous tutorial 6, and also the CP value. And we need to determine how much is the outlet temperature when we use 200 tubes. Okay, so far this is the complete drawing with the complete label. So let's have a look at the next step. So the next step is to calculate the area for one tube. Okay, so we have internal area and also outer surface area. So it is not the same anymore because we have different diameter. So for the internal area, you have 0.16, and for the outer area, you have 0.29. Okay. Then the next step is to calculate the R and total R. So R is the resistance and total resistance without fouling. So look here. So because I draw only one tube, so I calculate area for one tube only. And the resistance should be actually So we look where the direction of heat transfer, because the surrounding is hotter than the inside flow, because here the inlet temperature of the shell is 160. So Q is from the outside to the inside tube. So that means we have R1 here at the shell side, R2 due to the conduction, and R3 is due to convection inside the tube. So using this formula, this is for convective, this is for conduction, and this is also for convection. Because I draw for one tube, I would like to find the resistance also per one tube as my basis. Okay, then I get the total resistance of these three. And this is without fouling. Okay, without any fouling, we have only three resistance. Then what is next? The next is actually to find the overall coefficient, also based on my basis of one tube. Okay, so because my area just now is 0.16 and my total resistance is 0.0377, so I get overall coefficient. Okay, because this is the formula for overall coefficient. Okay, so I get 182 for inside overall coefficient and 118 for the outside overall coefficient. Okay, so far this is first step. Okay, this is first step, second step, third step, and fourth step. So far I have discussed till step number 4. So until step number 4, I still use the basis of one tube for the calculation. Okay. Now you want to calculate for effectiveness. Okay, as I mentioned, effectiveness will be increased. This is already expected because you have higher surface area. Okay, so for 200 tubes, therefore starting from this one, okay, which is step number 5, okay, I will calculate it using 200 tubes. So now you see that for 200 tubes, you multiply the inside area and outside area with 200. And this should be the answer. Okay, then you also need to find the value of C min and C max, which you can find from the value of Cc and Ch. Okay, Cc means the mass flow rate of the cooling fluid multiplied with the heat capacity of the cooling fluid, and Ch means the mass rate of heating fluid multiplied with the heat capacity of heating fluid. So from here, you know that this is not changed. This part hasn't changed. This part is actually from tutorial 6. Okay, it hasn't changed. So because mass flow rate you keep maintain the same, okay, only the arrangement are different. Okay, so that means you can calculate the C min over C max ratio, and this gives you 0.6. So this is also the same as tutorial 6. Now you want to find the effectiveness. So since you have the Cmin over Cmax ratio, okay, you also have the value of total area and also the overall coefficient. Okay, this value is known, this value is also known, and this value is also known. Okay, then you can calculate NTU. Okay, now you are wondering how you can get NTU, of course, from graph, but which graph? So the question specifically said it is one-to-one layout. So please refer, okay, in your textbook, please refer page 'This NTU. Okay, it is counter flow. Sorry, it is counter flow and it is one-to-one layout. So you can refer to graph 4.9 dash 4.9 dash 7A. Okay. From here, try to look on your own, and I have look on my own, and I get the effectiveness of 0.58. Okay. So now you know the effectiveness. What is the next things? Okay, so that means you have already answered this part. Okay, let me. Okay, you have answered this part already. Okay, so heat transfer rate, new heat transfer rate need to be calculated. So how to calculate this? Okay, so just now you have step 5. Here is step 6. Okay, so you want to calculate Q. Q is the effectiveness multiplied with the Qmax. Okay, Qmax is same like last time. Okay, because Qmax is the maximum of the heat exchanger, which cannot be reached by any means. So that means it doesn't matter about the arrangement. If you have specified the temperature and also the rate, and the mass flow rate and the heat capacity, so that means this is actually your Qmax. Okay, this is actually your Qmax. So your Qmax is basically the same. Okay, so what is not the same here is the effectiveness, which is 0.58. Okay, so please refer to your tutorial 6. What was your effectiveness for that one? Okay, so here the Q value you will get is 400,000 watt. Okay, which is higher than last time. Because last time, so sorry, this is not tutorial 7, this is tutorial 6. Last time for tutorial 6, I think it's about only 300,000, right? Watt. Okay, so this shows that with the increasing number of tubes, the rate of heat transfer also increase. Okay, that means you have with the same time, okay, because this is joule per second, right? So with the same time, with the same second, you can transfer 400,000 joule. But for tutorial 6, the one with only one tube, you can transfer only 300,000 watt or 300,000 joule in 1 second. So you have higher rate of heat transfer with increasing number of tubes. Okay, last but not least, not last, but the second last, I think, calculate the outlet temperature. How can you calculate the outlet temperature? Yes, by using mass balance, right? So Q, okay, the actual Q is actually the Q of heating or cooling fluid. So if QH, so you can multiply with CH, because CH is the inlet, no, not the inlet, the inlet rate of mass of heating fluid multiply with its heat capacity. Then, and so this is like the product of M and Cp multiply with the inlet and outlet temperature of heating fluid. So this one is unknown here, the rest is known. Okay, THO is unknown. So you get TH out is 101.2. So oh yes, I need to calculate both, right? For this is TH out. So one moment. I need to calculate also for TC out. Okay, if I calculate it somewhere. Oh, I forgot to calculate it. Okay, let's calculate it together. So if this is for TH out, what about for TC out? For TC out, I take for 299.2 divided by 5016. Plus 20. Okay, actually, this value here is not value of TH out, but it is the value of TC out. Okay, my mistake here. Because this value, if you press calculator, it will give you different answer. So 407 299.2 divided by 8620. So 160 minus answer. So TH out is actually, if I recalculate, TH out is actually 112.7 degree Celsius. Okay, but for TC out is actually 101.2. So this shows that not only it gives you the higher rate of heat transfer, but it also gives you, or it also increases the outlet temperature of cooling fluid. So from tutorial 6, the outlet temperature of cooling fluid was 80 degree. So when you use 200 tubes, you increase it to 101.2 degrees C. Okay, so next step is step number 8. Okay, so if you remember or if you forget, let's go back. So maybe we can finally sketch the illustration zooming to one tube of the total resistance if fouling occurs on the tube and shell side of heat exchanger. So let's have a look. So now total resistance should be 5. Okay, so this is one tube. Okay, if I divide it into half, so here you have resistance 1. Okay, resistance 1 is due to convection at the shell side. Okay, then this is R due to the wall, and this is fouling on the shell side. Okay. Oh, I think I draw it wrongly. It should not be here actually. It should be here. Okay. The fouling on the shell side. Okay. It is not in between here. Cannot be. Okay. Pardon me, my mistake. So let's make some correction here. So here, actually the fouling is not here for the shell side. The fouling is this one. Okay. The fouling is this one at the shell side. So therefore, we have R1 as the convection at the shell side, and we have here here is fouling at the shell side, so we have RFS. Okay, then we have the wall here, so we have the third resistance. Then the fourth resistance is the fouling on the tube side, and finally we have the resistance at the due to convection inside the tube. So that means this is 1, 2, Fs is the on the shell side. This is due to wall because conduction. Then resistance at the fouling tube side, and finally the resistance due to convection inside the tube. Okay, so to conclude, when you have fouling, you increase the number of resistance, and the value of overall coefficient will also be changed. Okay, so I think I should finish till now. Okay, maybe I can continue later with part 3 for the discussion on the tutorial. So with that, thank you very much.